Taking care of recording.
Great. All right. So welcome back, everyone. I hope that you're well. Let's continue from where we left yesterday. Excuse me. Just let me quickly recall one or two things we said yesterday. So we studied the scalar denoising problem, which is a very simple inference problem, which is just about denoising a scalar signal x star, a scalar variable x star, which is corrupted by additive Gaussian noise, and therefore the data, which is a single number, is our signal times the square root of the signal to noise ratio plus Gaussian noise, okay? Which is equivalent, of course, to say that y, our observation, is just drawn from a Gaussian variance is 1, and we're trying to recover the mean, essentially x star, okay? And what we've seen is that we can derive the IMMSE formula. I mean, I haven't given the details there, but this is your job to check at the proof. It's not complicated. But with the final formulas for the MMSE, which are explicit for the Gaussian and Rademacher case, for example, for the Rademacher case, this is the formula for the MMSE as a function of lambda. We can draw this MMSE, the best error you can achieve in this reconstruction problem, as a function of the SNR. And what we've noticed is that the curves are not so interesting. There are no non-analyticity, no discontinuities, nothing very interesting happens. It's just a smooth decreasing curve in both cases, with the Rademacher curve being below, because the Rademacher prior is, of course, a more informative prior than the Gaussian. It constrains more your signal, okay? Perfect. So what we said is the reason why these curves are not so interesting is because there is no complexity. What we need is to consider inference problems where we aim at reconstructing a large number of parameters. So we want to be in the high dimensional setting. And these unknown parameters should somehow be coupled, should depend on each other through our observations. And this is where the Spike-Wigner model enters. So in the Spike-Wigner model, every observation is about not anymore a single component of a vector, but it's about two components. It contains information about two components, and therefore it introduces a coupling, because each observation is a function of two components, and therefore you have dependencies. So it's the product of two components of our unknown vector, xi star, xj star, multiplied by the signal to noise ratio square root lambda, divided by square root of n. I will say why this square root of n is important, plus Gaussian noise, okay? And the inference task is given all these pairwise measurements, these yij's for every I less than j. Can you reconstruct x star, which you do not know, and of course you do not know the noise z as well. You just know the functional form of these observations. You know that yij was constructed in this way, but you have to reconstruct x star, okay? Perfect. So we will see in this lecture that this 1 over square root of n is important. The reason basically is that this is a matrix that we call a Wigner matrix. We will study it today, and it has a certain spectral norm. So basically its spectrum of eigenvalues has a certain support, and somehow this scaling there is such that this matrix, which is a rank 1 matrix, concave as a function of the SNR. And for such sequences, the limit and the derivative obtained by solving this consistency equation. And this is just a scalar given square root lambda q x star plus z. Okay? So you solve this consistency equation. Maybe there is only one solution, then you pick it. Maybe there are more than one solution, then you need to find the one that minimizes this potential, this function. And once you pick it, you plug it in this very simple formula, rho squared minus q0 squared, and you have access to the MMSE. So now we have an explicit formula for the best error, the best reconstruction error, the base optimal reconstruction error on this rank 1 spike. Okay? So you can try any algorithm in the universe, whether it is efficient or it takes infinite time to run because you want it to be as precise as possible. You cannot beat this mean square error. This is the best you can do because this is the best estimator that exists. It's the Bayesian estimator. We have proven by Bayesian decision theory that is the best. Okay? Okay. So I will move on. If there are no questions, if there is a question, just ask. Okay.
Yes, sir. I have a question.
Yes. Go ahead.
Last statement like this one. So I wanted to know, like for each and every time, like whatever we are the theorem or the formula we are using, like for this limit and tending to positive infinity, 1/n². So like how the algorithm works for the infinity terms, because there should be kind of a limiting parameter, like using infinity itself. uh, there, there must be a parameter so that will limit the constraints and the noise and each and everything. So that's what I am wanted to get know from this, like how can we understand this?
I'm sorry, your question is not very clear, but what you mentioned is algorithm.
Yeah.
Here, what I'm saying, there is no algorithm. What I say is a theoretical result. Of course, we are considering these infinite size limits. So this is purely a theoretical result, right? So in practice, so I want to say two things. The first thing you see is that I'm taking limits when the system size grows. So conceptually, what I'm saying is that I'm considering the inference problem for a certain size. Then I increase the size, kind of regenerate an instance of this Spike-Wigner model, but of a slightly bigger size. So I have more unknowns and more data, which are both controlled by n. And I do that for n, which is increasing. And so I'm considering a sequence of problems, okay? And I'm studying how, what is the mutual information and the MMSC for this sequence of problems when the problem size becomes very large, and it's given by this, okay? In practice, this is of course not the case. In practice, you have the problem, which is for a given size, let's say n equal 1000, and that's it. You have the data in your hand, and you cannot increase or decrease the problem size. You cannot do anything. You just have the data, and you want to make inference, right? So how do the two relate? The point is that what you can prove in this type of problems, very generically, is that you have so-called concentration. What does it mean? It means that if for a given size, a finite size n equal to, let's say, 1000, which is large but not too large, it's realistic. You're trying to solve the Spike-Wigner model with an actual algorithm, okay? And you compute the error. Let's say you're doing this in a theoretical setting where you have access to the unknown parameters just to compare with your estimator. You're making an experiment. And you compute the error that your algorithm obtained. And you compare this to this quantity, which is instead the error predicted for the infinite size limit. They will be very close. This is what concentration means. It means that this quantity without the limit, without the limit, so for a given n, even without the expectation, you can remove the expectation. This object, which is really the concrete, the explicit minimum mean square error for your problem, will be very close, and by very, I mean with an error that is of order 1 over n or something of this sort. It will be very close to this object, which is the theoretical prediction, where we took an expectation with all possible realizations of the problem, and we took also a limit when n is infinity. But somehow the finite size version of this object and the infinite size theoretical prediction will be very close when n is not small, okay? So this is why this kind of asymptotic formulas are useful also to understand concrete, practical, finite size problems. It's what we call concentration, okay? I hope it answers your question.
Got it. Yeah, thank you.
This is a very important point. Thank you for asking. It was very, I should have mentioned that earlier, because for me it's something a bit obvious, but of course it is far from being obvious. I will mention that point more. Okay, so now we have these formulas. Let's exploit them and draw what we call a phase diagram in physics, okay? Phase diagram is, maybe you've not heard about phase diagram if you haven't studied physics, but you've seen phase diagrams if you come from electrical engineering, from most of you have seen somehow versions of phase diagram. They were just not called phase diagram. It's just how physicists call it. It's just a figure that tells you as a function of what we call a control parameter. The control parameter here is the signal-to-noise ratio. So the control parameter is somehow a quantity you should imagine that in a experimental setting is something you can tune, you can control, okay, and change and see how the problem behaves as a function of this parameter. And the object that you are interested to analyze, to understand as a function of this control parameter is called in physics the order parameter. It describes the problem. And the order parameter is in the context of inference is the mean square error. It's the reconstruction error that quantifies how good is your estimator for the unknown parameters. Okay? So phase diagram is plotting how an order parameter, the MSE, changes as a function of the control parameter, the signal-to-noise ratio. And with these replica formulas, now we can plot explicitly the MSE as a function of lambda. And what happens, so forget this at the moment, I will explain it later today, is this picture. It is really the main conceptual point of all this course is to understand what this means, okay? Because here, this phase diagram is plotted there for the spike-Wigner model, but what I'm going to describe now is extremely general for high-dimensional inference problem, for high-dimensional learning problems in machine learning. It's a very generic picture, okay? The exact values where this the exact value of these curves or the exact value at which they change like this, of course, is problem dependent. But the presence of these different regions that I'm going to describe now is very generic. Okay? Okay, so let's see what they mean. So I'm plotting three curves. The first curve in black is characterizing the performance of the Bayesian optimal algorithm. Okay, this is what I mean here. So this is the minimum mean square error performance. So this black curve is the best error that any algorithm can reach. It's the information theoretic bound, okay, on the performance. The blue curve, dashed, will be the performance of a practical algorithm that you can use for a given problem, and we're going to study today. It's called spectral PCA. PCA is for principal component analysis. This is a spectral algorithm in the sense that it will be based on diagonalizing the data matrix and looking at its eigenvectors. So it's based on the spectral decomposition of the data. And the third in red is a Bayesian algorithm, like the optimal algorithm. The optimal algorithm is essentially computing the posterior mean, which is fully Bayesian. This is also a Bayesian algorithm, but which is trying therefore to compute the posterior mean, but not by brute force. It's trying to compute the posterior mean in a computationally efficient way. Instead, you see, what do I mean by brute force? Brute force, so the posterior mean, to reconstruct the spike. So the base optimal estimator is this. And this concretely is an integral over R to the n, which is the dimension of our vector, of x transpose, which is an n by n matrix, of the posterior distribution of x given y, which we wrote before for the spike-Wigner model. And you need to integrate over x. So you see this is an integral over a very high dimensional space. So you would need to sum over a volume that grows exponentially with n. And this takes forever, of course, when n is large. You cannot compute this integral explicitly. There is no way, right? Maybe you can approximate it by doing Monte Carlo. You can use smart algorithms, but these are algorithms. Maybe they work, maybe they don't. Computing this exactly is in general not possible, okay, due to this high dimensional integral. But if you were doing so, information theory tells you that you would get this performance in black, okay? We computed this through theoretical tools when n is large. Instead, the red curve, this Bayesian algorithm called AMP, that stands for approximate message passing, is trying to approximate this expectation as an estimator, but not through a Monte Carlo, not by sampling this space. It's doing something else that we're going to discuss a bit. And you see that it has another performance which can match the base optimal one, but it requires a bigger signal-to-noise ratio. There is a region there where they do not match. So let's discuss these regions. The first region is called statistically impossible, in the sense that even the best algorithm in the universe leads a very poor performance. So let's say that this is 1 here, is the highest possible mean square error. This is the trivial error that you get if you always output the all zero vector. So it's the most stupid algorithm that exists. And the base optimal algorithm is matching the performance of the most stupid algorithm in the universe. It means that there is not enough information in the data matrix Y to say anything about the unknown parameters. So it is statistically impossible, and the statistically emphasize here that it's not a computational barrier. It's really a fundamental lack of information in the data to recover the unknown parameters. Okay? It's information theoretically impossible to recover the parameters in these regions, in this region of signal-to-noise ratio. Here the SNR is too small. So the inference problem in this region is doom. You cannot do anything, okay? Then, if the signal-to-noise ratio becomes bigger than this threshold here, that we call the lambda IT for information theoretic, it's called the information theoretic threshold, the MMSE starts being non-trivial. It's not 1 anymore. It's something smaller, okay? And you see that here the transition between at this threshold in the curve is discontinuous. So now we have a discontinuous behavior. You remember in the denoising problem, as a function of the SNR, the curve was very boring. It was this curve. Okay? No discontinuity, nothing interesting. Now we have discontinuities and interesting behavior that we call phase transitions in physics or threshold phenomena in computer science, because the problem is complex. You have interactions between many variables, and very concretely from the replica formula, what happens at this transition, at the level of the formula we looked at, what happens there? You remember that the Q, the parameter entering the replica formula that allows us to, that we need to find the minimizer of it, that we need to plug in this replica symmetric potential, this function, to find the mutual information and the MMSE. This Q0, which is the minimizer, was given by this consistency equation. So you try to solve this equation, and basically what happens is that here the only solution is Q0 equals 0, which implies that the mean square error is 1. And here this Q0 is still a solution, but there exists another solution, which is the one minimizing this replica potential, this function you need to minimize. So you see, it's like if you have a function which is this replica potential. Let's call it IRS for replica symmetric, and the same notation that I used, of Q. And it looks like this. In this region, it has a single minimum at Q equals 0. And so it's the only one, you need to pick it, and it gives MMS equal to 1. But in this region, at some point when you approach this SNR, because it's also a function of lambda, but here I'm plotting it as a function of Q at given lambda. When you approach this value of SNR close to the IT, it starts to have a second minimum that appears, a local minimum, okay? But it becomes the global minimum, so it goes down as Q, as lambda increase. And at some point, this local minimum becomes the global minimum, exactly at this transition. And now you need to pick this value. This is the recipe of the replica formula. You need to pick the minimizer of this function. And so you see you have a discontinuity. You go from something which is strictly equal to 0, there, to something which is strictly above 0. This is how it generates a discontinuity in the behavior of this function. Okay? This is what we call in physics a first order transition. It's when the order parameter, the statistic of interest, has a discontinuous behavior as a function of the control parameter, here the SNR. It's called first order transition in the sense that the first derivative of the mutual information, which is the MMSE, is discontinuous. Okay? So this is how, even if somehow the high dimensional problem collapses to the study of a low dimensional scalar denoising problem, you can still have non-trivial behavior, discontinuities, because you need to solve this kind of self-consistency equation that can have multiple solutions. And at some point, you have an exchange between the minimizer, between two solutions. And so it induces a discontinuity. Okay? Okay. So what is now this region beyond this information theoretic threshold, where the minimizer of the replica potential becomes a Q which is not 0 anymore? It means you can reconstruct. This is a region which we call algorithmically hard. Why? Because this is a region where even if the minimum mean square error is not 1, so it means information theoretically there is enough information in the data to reconstruct the signal, the unknowns. We do not know any efficient algorithms that are able to do so. If we take the best algorithms we know, which are these two, they still give a very bad error equal to 1, as if you were still in this region. So they are not able to extract the hidden information in the data, even if it's present, but they cannot extract it simply because they are not smart enough. We believe that in this region, the only way to get such an error is to explicitly compute this integral, which of course takes a time which grows exponentially with n. So this is not efficient. When the computational complexity of your algorithm grows exponentially with the size, with the number of unknowns, it is said to be non-computable, not efficient. It's too costly. If it's not exponential, if it's polynomial in n, then the algorithm is said to be efficient. These are two polynomial algorithms. This is an exponential algorithm. This is exponential n, the complexity, while this is polynomial in n. Both. Okay, so this is a very, very important point. The presence of algorithmically hard phases. Okay, it's called a phase also, again, with the vocabulary coming from physics. This is a algorithmically hard region or phase. This is the same. Okay, beyond this information theoretic threshold. But at some point, if you continue to increase the quality of the data in the sense that the signal to noise ratio becomes larger, the signal part in the data becomes more and more strong compared to the noise, at some point you enter the so-called algorithmically easy region. What does it mean? As the name suggests, it means that now we have an efficient algorithm in the sense that the number of operations it needs to do to output an estimator is polynomial in the size, such an efficient algorithm is now able to match the performance of the minimum mean square estimator, which in general is exponential. Okay? So this is what we mean. With polynomial time, polynomial cost algorithm, we can match the performance of in general exponential time requiring algorithm, which is this one. So it's algorithmically easy to find the optimal estimator. Okay? And so here we see a difference between these two algorithms. We see that the spectral, the Bayesian algorithm AMP suddenly goes from very bad, from trivial estimation, which essentially always output the all zero vector, to perfect performance, in the sense of optimal performance, base optimal performance, again with a discontinuous transition. Okay, it's a sharp transition. Instead, the spectral algorithm, PCA, which is much simpler, we're going to discuss it, is also changing behavior at the same transition, but it's not optimal. It gives a non-trivial estimation, a non-trivial error. It's not one anymore, but it's not matching the base optimal performance. Still, it's an efficient algorithm that you can use. Okay? But if you have access instead here to this AMP algorithm, you should use it because it gives something much better. And we will see that the reason why these two algorithms do not give the same is that they're very different classes of algorithm. In particular, the spectral algorithm, PCA, does not exploit the prior knowledge about the distribution of X star. I haven't mentioned it, I'm sorry. Here, this picture is for a given prior of the signal. The Xi stars are drawn from a given prior. And this given prior is a sum of two Diracs. It's not Rademacher, it's different, but essentially these components can take just two possible values, A and B, with a different weight. And if you choose A and B in the correct manner, you obtain this picture. Okay? The Bayesian algorithm, like this AMP and of course the MMSE estimator, they do exploit correctly this knowledge. Not of X star, of course, you don't know X star, but the knowledge that the entries of X star were drawn from this prior. So they exploit the correct prior. The spectral algorithm does not exploit the prior. That's the difference. So you lose, you pay the price in terms of performance. Okay? Okay, can I move on? So this is conceptually very rich, this picture. Is there something I should repeat? Okay. We started at what time? Jaspal, for how long have I been talking? An hour and 15 minutes, something like this, no?
Sir, the time for the lecture has completed. If you wish to continue for 1-2 minutes to wind up, we can, and then we can resume back in the another lecture that is scheduled, I think, at 2:30 p.m. today.
Yes. Okay. I think this is a good point to stop. I think the students have quite a bit to digest conceptually here. And we can continue later then. So the next lectures we're going to start. So let me just lay down the goal for the two lectures of today. I will try to give you some techniques we're going basically to analyze this blue line. We're going to analyze to provide tools from what we call random matrix theory to understand the performance of this first algorithm, PCA. So conceptually, what we've done now is to, we haven't analyzed, but we have discussed the optimal performance through Bayesian decision theory, and then I gave you the replica formula that we're going to derive in 2 days. But we discussed mostly this thing. This afternoon, we're going to discuss this thing, which is a concrete algorithm you can use for the problem, okay? And it will lead this performance, okay, instead of that one. So we're going to study this in a bit more detail, okay? Sorry, and I forgot to mention that one important point, the threshold here at which algorithms starts to perform well is of course called the algorithmic threshold, in contrast with the information theoretic threshold, where the base optimal estimator becomes non-trivial, okay? This is instead the threshold at which the best efficient algorithm becomes non-trivial. And in this case, the algorithmic threshold, of course, this may depend on which algorithm you're talking about, and in general it does. The best algorithm that we know for this problem is this AMP algorithm. So this algorithmic threshold is essentially the threshold of this AMP algorithm. But it actually also corresponds to the threshold of this PCA algorithm, because they become non-trivial at the same location. But in general, it could not be the case. They could have different algorithms, could have their own thresholds. And the threshold for the PCA algorithm is not called lambda PCA, but it's called BBP, for the name of Benahous, Baik, and Péché, 3 mathematicians that precisely studied the behavior of this algorithm, and as we're going to do this afternoon. Okay, so see you in what time do we resume? At 2:30 for you.
2 hours, after 2 hours.
In 2 hours. Okay, perfect. Goodbye.
Okay, thank you. I thank Dr. Jan Barbier to spend the time, and I thank all the participants. So I hope, is there any questions? I shared the PDF also in the group yesterday, and also we are having YouTube live link also, that I have shared. So with these words, I again thank Dr. Jan Barbier and all the participants for patient hearing, and we will join back at 2:40 after 2 hours now. Okay, thank you.
Yes, see you.
Thank you.